So this is the infodynamics paper, and it still has the old date on it. Right. So this was in some ways a very conceptual paper. They began by discussing expectation as trying to move the videos out of the way here. The expectation as sort of a fundamental part of the musical experience. So expectation maybe as a particular kind of tension and resolution paradigm, but expectation and then fulfillment or surprise. So this happens in time, and in other words, maybe there's some storing of information in memory, but it's very much, expectation is very much a time-based sort of phenomenon. And they do discuss, for example, how it draws from familiarity with stylistic norms as well as our short-term memory as we listen to the piece. So they began with this very philosophical sort of discussion. And the approach that they took was to, because this is sort of a very general philosophical notion, expectation in music, they adopted a probabilistic model there, and then a probabilistic model of music, where pieces of the music come from these probability distributions, and then they described the dynamics of the music coming from these probability distributions using information theory. So this is how information comes in from this underlying probabilistic model. And also they took a subjective approach. So this is, admittedly, they claim that this was sort of a subjective approach to describe the listener's experience of expectation, but I found it also, of course, very much statistically based. So sort of, I found it intrinsic in many ways. So that actually will tie to some of the notes at the end of this presentation, sort of the criticism of the extent, which I mean, there's an extent for all of our papers, and I think the extent of this paper, as we'll see, is that it's a purely formal description of music that they're investigating here, not the sound itself, which I think would actually connect a lot to Daniel's presentation, and which is fresh in my memory, but and also people's previous presentations on EEGs and things like this, because that's really what's happening in our brains, and not necessarily the formal aspects, but this is in some ways the only way to grapple with it, to simplify this complex situation. So in some ways, this was a very simple paper as a sort of island or oasis in much more complex sort of, well, the analogy doesn't hold. It's a jungle, but it's not exactly a desert, is it? So the background objectives that they stated were to propose information-based measures of how to describe this information stream that's coming at us in time, and what really are we, what information are we getting from this real-time stream. And then they hope to engage with computational models of the listening brain, which that would be the axis along which people connect to the Bayesian brain, and all these other cognitive and neurological studies. And then there's another axis that explores computational models of aesthetic aspects. That's sort of my paraphrasing, but they really mean formal structure. So this paper, just to summarize this introduction, is not about sound. It's about the formal aspects of the composition. And you'll see that that's why they chose minimalist music, because they can represent it very formally, clearly. And I'm actually excited about how this would be applied to sound. And let me see how to move these here. I'm not sure if you can hear my cat meowing. 3 probabilistic models are assumed. So like I said, there's an underlying probabilistic model of music. I mean, probabilistic meaning that there are these sets, and from these sets, there's, events, really, is how I learned or thought of them. And so there's I suppose I didn't include any graphs or equations, so no mathematics graces my slides. But let me see if I can share the paper. I had it up for the for this. Uh-oh, I don't know what happened. Well, let me stop sharing because it's not quite sharing anything. Okay. Oh, no, that's not. Yeah, this is my slides. No, that's not. Hold on a moment. Zoom always has a little difficulty with all these windows. Oh, I see. Sorry, just a moment. I actually have also the music up so that we can listen to it. Jeez, I don't want to see that. So the yes, so I only wanted to show one graph. That was the graph, but I mean, everyone has lots of nice visuals, so I think I'll just show this anyway. I'll change my mind. So they have these probability distributions, and understanding this is where all the this is really the foundations of this this information-based approach. In general, I believe information theory is based on a probabilistic model, and I mean, there's lots of people. One can refer to like Tinshin's discussion of probabilistic foundations of information theory. But so they say that the that there is a finite present set of elements of our music, and then there is a infinite past and an infinite future. So these are actually infinite sets here. Z is the past and Y is the future, and X is the present. I'll avoid getting into too much of those equations, but that's helpful to know. There's a finite present set of elements and or events in music. So they, from this, as soon as you define that, just say that there's a set of events that the listener is hearing at the moment. In other words, I'm sitting listening to my cat meow, and I'm hearing a finite set of events, I guess, and there's an infinite future of cat meows, an infinite past of cat meows as well. And this is the once you have this sort of framework, you can start discussing information measures. So they begin with surprise-based measures, which are the simplest. And I left out a nice equation, but because I think it might weigh a bit. But well, I'll just continue with what I have here. The surprise-based measures that they proposed, really they invented everything. So the surprise-based measures are conceptually how expected is the present stuff that we're hearing based on the past stuff that we've heard, and they ignore the future. So the negative log probability is the surprise. It's really very intuitive, actually. Probability, I'm sure you know, goes from 0 to 1 inclusively, and then take the log of that, you get negative infinity to 0, or yeah. And then if you flip that, you get positive infinity to 0. So in other words, they're just mapping our probabilities 0 to 1 to positive infinity to 0. The fact that it's log doesn't really, I mean, I think maybe you can think of it as bookkeeping, although I'm sure there's a deeper explanation of that. But really, in other words, what that means is we've now mapped 0 to positive infinity, which means if there's no probability that something happens, like seeing a unicorn walk into the building, then you will be infinitely surprised. That's what they're defining surprise as. And they say if there's 100% probability that it'll rain or that someone will get elected, then you will be 0 surprised. So that's what negative log means. That's just sort of a simple way of thinking of it. It's mapping 0 and 1 to infinity and 0. So the negative log probability of the specific present given the specific past. So if you take a specific event in the present and a specific event in the past, what is the surprise of the present event given the past? And the specific I think he's hungry. Just a moment. Well, he ran away. The specific present given the whole past is the other measure that they defined. They defined 4, and really it's just this recurring pattern of specific events and the entire set of events. And I mean, one can get into the equations, but this is what it means, or at least if I'm interpreting these variables correctly. Whole present given the specific past, and the whole present given the whole past. And so I mean, that should be intuitive. I mean, you can talk about the surprise of something given everything you've heard, or the surprise of something really only one particular thing you've heard, like if you've heard a lot of stuff in the past of some if you hear the first movement of I don't know, if you hear the opening subject of a fugue, then you know that that subject is really what prepares you for the future information. You know that the rest of this piece is going to have a lot of that recurring, and not exactly other stuff, but that particularly. So I mean, if I'm interpreting this conceptually right, that's what it means. That's all about surprised about what the present is. That's really a way of evaluating the present given the past. But the predictive information-based measures are a sort of new. That's what they, I guess, introduced this additional feature set probability distribution. They are measures of how much information the present and past convey about an unknown future. So the way that they do this really is simply the mutual information shared between the future and the past. So we're sort of presupposing we already know the future. So this is a model assuming that you're already working with the whole picture, but you can't. I don't believe you can calculate this without having that future, which is an interesting limit in this of this approach. I don't know if you can talk about predictive information if you don't know what it's predicting, or and so you sort of have to know the future to look back and say what the past and present said about the future. And the way they do it is the Kullback-Leibler difference. It's actually, I think, I never know how to pronounce the names, so I won't get into that. I think Daniel covered it actually, which is probably better than if I do. So I'll just skip. He had the equations, so that actually might be helpful for this definition. I just call it mutual information here to keep it conceptual. The specific present given specific past. Yes, so it's the same thing over again, but I mean past here to include the present, I suppose. So that is predictive, which should be intuitive. I mean, predictive means what you're actually predicting in the future. And surprise means you've already been surprised. The information, yes, okay. So they also define these model-based measures, which are given an explicitly parameterized model. What are the information rate of these parameters over time? Which is really just simply, you know, if you have granulation parameters or something, there's an information rate associated with your grain parameters like grain duration, trigger, trigger time, and you know, sampling and position and all these things, and envelopes, amplitude, and whatever. So these are all model-based measures, which are directly, you know that from the they're sort of given. And then they mention Professor Dubnoff's information rate. So he's famous, and mutual information shared between the whole past and whole present. And I think there's some discussion here which they refer to. So I wanted to, but they try to interpret his measure in the context of their framework. And so they say that it's the mutual information shared between the whole past and the whole present, I believe. And let me find the exact sentence. Yes. Yes, I'll try to avoid the too much of the technical details. But So this is the mutual information between the whole past and whole present, which they call the redundancy. And so really what they've collected are these 9 or 10 measures of information, and they're all in terms of entropy and conditional probabilities, which is very that's just information theory. But the way that they applied this to music is what is novel and innovative. So the authors primarily focus on these as measures of structure, not sound signals themselves, which I was actually surprised by, but it's structure. And in other words, some sort of symbolic representation of this music. The interest, oh yes, also, so they say that interest follows an inverted U shape, and we've talked about this in, I think, previously. And well, I suppose I have the paper right here, so I'll just show you. It's a little, hopefully that's clear. This is the inverted U relationship between goodness of the music and whether it's deterministic or random. And they claim that listeners find music that's too predictable to be boring, but if it's too unstructured, like white noise, then it's also boring because we can't really extract any patterns from it, and it, to us, becomes filtered out as noise in the same way perhaps that repetition gets filtered out. So there is some sweet spot, I guess they say, right in the maximum of this inverted U function, which is the right balance of both. And what I found interesting is that they say that over time, repeated listenings or repeated exposure, they say one's value change in one's value judgment shifts to the left. So that makes sense because if you hear, I don't know, everyone's here already has heard everything ever, So I can't really, there's no surprising names, I don't believe, but back when Stockhausen was surprising, if you listen to him many times, maybe you would find him less surprising in the repeated listenings. Maybe it's the same with Bach, actually, since he was described as, his music was described as turgid. So dense information is upon repeated listenings. So they discuss these sort of additional conceptual considerations. Yes, I just said this. Yes, I just said that. Oh, yes. And so the way that they, the first example with which they studied the first example they applied these measures to was Markov chains. I have a point here, which I didn't have a chance to write. This wasn't quite involved mathematically, so I just will say that the idea was that a Markov chain, as we've covered in class, well, okay, since it's such a nice way of saying it, they use a transition matrix to encode all the probabilities of one state moving to another state, which I thought was nice. I think that might be some, in the literature, that's the what they use, transition matrix. And so you can define the these measures in terms of probabilities from this transition matrix. the point I was going to add here is that they discuss knowing the current state and the state directly preceding, prior. So you have the past, one state in the past, and the current state, and then that's how you predict the future state. That's what they claim for the predictive information rate. And then I believe Shlomo's is they discussed this as well in the later sections as I had written it down, but I believe, if I'm saying this right, of the past state with the present state. So there's a way of calculating these measures for Markov chains given this probabilities in this transition matrix, and yes, and their findings were actually, yes, they were here. I wasn't sure if I should include all of these things. Let me see. These are the equations. I believe this might take a little while to explain, so I won't. But it's nice to see. And these are the what I'd like to say about it is that the measures correspond with changes in the system that we do intuitively interpret as being surprising. I tried not to focus too much on the Markov chains because that was in some ways a test run. They were modeling music as a Markov chain, so to test these measures on. So it's yes, actually, why don't I just play this right now, because before I talk about them, that will be helpful. So they were analyzing what's his name? Philip Glass's 2 pages, which is solo, and for some solo instrument. I don't think it's specified because I've seen it for piano and marimba. And then this is now the time when I need the microphone to go through.
I'm not sure you shared the sound. Oh, you still didn't play the video. Okay, yeah, thank you.
Okay, I just wanted to play a brief sample of this so you get a sense of the piece. Hopefully everyone heard. And that, so there's one, yes, solo and regular, right? So the word I used was isynchronous, which means every note is the same length. So that what you just heard continues for another 17 minutes, and but what changes in this piece are the configuration of the notes, and there's a similar piece, Gradus. I don't actually know if that. I think they simplified it as asynchronous, but they discussed how they modeled these in the paper. All this is discussed in the paper, methods and so forth. But ultimately, what they did was they reduced these to scores, I guess you can say, to symbols. So they reduced these to strings of symbols. I suppose I can show you. Yeah, it's something else. Huh. Well, I seem to have lost where my paper was. Doesn't matter. They, oh yes, okay, I was going to show you the paper now. Hold on. Yes, this is the paper. Oh no, is it? Hold on. Oh yes, okay. This is the paper, and this is the string. Oh, oh no, I'm keeping. Oh, let's see, just oh, this is on the next page. Yes, this is the string, and this isn't, of course, the piece. I don't believe, but this is how they represented it, and there was, yes, this is actually something I wanted to say, that their Markov chain thought that only a change in the pattern, a change in the immediate pattern was surprising. But of course, when a human listens to this piece, if you listen to it long enough, you'll internalize some of the patterns as being in groups of 4. So we'll internalize 4 as being a pattern. And what's surprising is when we actually hear a 5th repetition later on. So hearing a 5th repetition is what is surprising. And that isn't captured, I don't believe, in these measures, because, well, a 5th repetition would seem to be less surprising. So they were discussing how there's actually something more going on in our brains, which of course makes sense. But what I wanted to show you in this was the graphs that they generated with these. So if this is the entire piece analyzed according to these four families of measures. So, and the structure of the piece does correspond with the measures that they proposed. The sudden changes in the pattern at the third section are they are in the score, really, and they're in this in this string, and the measure picks up that change in the pattern, really the immediate change. And actually, I'm really talking about the surprisedness here. But the predictive measures are, like I said, the past and present predicting the future. So when we hear the same thing happening a lot, I guess the predictiveness goes down. So we don't know what'll happen next. And then one can look at these graphs and interpret them many ways. Like, so I guess we become acclimated to some uncertainty, some things changing. So there's some increase in the predictiveness. But overall, it was very nice results. Oh, they also said that they had an expert listen to the piece. Oh yeah, it says them right there. And he marked off the surprising parts of the piece, and they corresponded to the model information rate, which is sort of the check verification that the score, that's what the model is, that this score actually does have in it clearly stated, explicitly stated, what are these drastic structural shifts. And so this was another sort of nice verification that these measures are actually measuring something that we're hearing. And I won't cover these things. They also analyzed gratis, but I won't discuss that too much. That's for saxophone, I believe. And they had a similar. It looks different because it's shorter. That's all. This is just a less compressed signal. But I have less to say actually about gratis, and because I think it's covered a lot in the first example. There's a final thing I wanted to say, then I'll wrap up. Oh yes, well they say stuff about future, about gestures and things like that. But where is it? No, that's not what I wanted to share. Yes, here. Hold on. Can't find. Where is? Here it is. Yes. Oh, well, okay. Yes, I guess all I had was thoughts. So the my thought on this was that it was certainly very effective in these proposed measures do correspond very clearly with what we're hearing, and so I think that is a successful approach to discuss if we know how to formalize the music in that sort of way, as symbols. And how to get there, I think, is sort of a difficult question. I'm not sure if this can be done directly with sound yet, but that would be my next thought of where to go with this, that if there's a way of discussing the entropy of a signal, or discussing that directly instead of with this sort of having the answer already, that we already know that, this is the we already have all the model parameters. So, but I think that that wasn't really the point of this paper. It was to establish these measures as valuable aesthetic descriptors. So they actually, these are these quantities, like a quantitative approach to aesthetic values. So, or they were able to quantify the surprise. So I think that since that was the goal of their paper, it was certainly very thought-provoking. Okay, I'm done.
Okay.